Hi everybody, this is lecture 16.1 on pressure. This is part B, atmospheric pressure. Alright, in this video we're going to look at a couple of things. First we're going to look generally at pressure in fluids. That includes both liquids and gases. We're going to look at hydrostatic pressure in water, and really more generalized hydrostatic pressure in all fluids, but we'll look at a special example in water. And then we're going to look at atmospheric pressure, talk about what that is, and finally we will look at the barometer. All right, so what is a fluid? All right, a fluid is really just something that flows or deforms when subjected to a force. And fluids don't have a fixed shape, but take on the shape of their container. And that phrase probably sounds familiar to you. Fluids, of course, include liquids. We've got a picture here of a whole bunch of liquids and glassware of different shapes, and in each case, the liquid fills up the glassware and occupies the same shape as the interior surface of the glassware, right? But fluids also include gases. So if we have a closed container here and this is full of gas molecules, the gas molecules are going to spread out and occupy this cylindrical shape in here, right? So fluids, in the kind of common vernacular, we think of fluids, we usually think of liquids, but fluids really means both liquids and gases. And that's going to be important for us because fluids have special properties with regard to pressure. And that's what we're going to look at here. All right, so here's how fluids are different and important. We did an example in a previous video where we had an iron bar sitting on a table, and we were calculating the pressure that the iron bar exerts on the table, right? If we look at this system, if we imagine someone pushing down on that that object, that cube, right? If you push down on it, that's going to create a force downward on that object, and then that object is going to transmit that force downward onto the table. And it's going to subject the table also to a force in the same direction. Okay? Now that's different from fluids, both gases and liquids. If we have a gas contained in the cylinder and we subject this to a force, if we push down on this piston and apply a force to this, instead of just a downward force, what happens is the pressure that we exert is going to get extended out in all directions. Okay. And this is known as Pascal's principle, which says that an external force exerted on a liquid is distributed, it says distributor, should be distributed, evenly throughout the fluid. Okay, here's an example. You may have seen these little toys that they sell, and if you have one of these, this is it's a hollow little toy, and inside it's filled with kind of a fluid gel, right? And if we were to put a force on this by squeezing it in the belly, right, then that force would be distributed all throughout the interior of this little object, and so we'd get a force pushing out in all directions, right? And you can see that if you actually take one of these and you squeeze it, right? The force that you created when you squeeze it is distributed out here, and it makes his eyes bulge out, it makes his ears pop out, and so on and so forth. That's just an example of Pascal's principle. The force being exerted here on the sides is being distributed evenly throughout that fluid. All right, so in the last one we were looking at pressure on the outside surfaces of a fluid, a liquid, or a gas, right? But if you have something submerged in a liquid, right, the liquid exerts pressure on the outsides of its container, but it also exerts pressure on anything that's submerged within it, right? And that's true of liquids, and it's also true of gases. So for example, if we had a little object inside this gas cylinder, I have a little cube in here, right? The gas would be exerting pressure on all of these exterior surfaces, but it would also be exerting pressure on the surface of this object that's submerged or surrounded by that gas. Okay? And this is the kind of pressure, well, both of these, this is the kind of pressure that we're going to be looking at in this particular lecture. All right, let's take a look at hydrostatic pressure. Hydrostatic pressure is a special kind of pressure, right, that arises in fluids, and it's not because of something else pushing on the fluid. Hydrostatic pressure is a result of essentially something pushing on itself. The hydrostatic pressure in a fluid comes from the weight of that fluid. Okay, you're probably familiar with the fact that if you're scuba diving or something and you're several meters below the surface, the pressure below the pressure underwater is higher than it is when you're standing out here, right? And so you have to do special things to protect yourself from that pressure. So let's say we've got this guy down here, and he is at a depth of, let's say, 25 meters. Okay. There's all this water up here above him, and all of that water is pushing down on him, and that creates pressure. Okay. We can figure out what the pressure is going to be by drawing a hypothetical surface here. So let's just draw a little area here. And you don't have to have an actual physical object in the water. You can just sketch a hypothetical plane of some area, and you can pick any area you want, 1 square foot, 1 square inch, 23 square feet, whatever you want. But let's take an area of 1 square meter, because that's part of the definition of pressure, and so 1 square meter would be useful. Okay. Now, if we want to know how heavy the water is that's pushing down on that 1 square meter surface, right, we just have to calculate the weight of all of the water above it. Right? So we can draw a kind of a rectangular prism. That's not a very good drawing, but I'm trying to draw there we go, that's a little bit better. There's this rectangular column of water, right, that is 25 meters tall and has a surface area of 1 square meter. Okay. We want to know what the weight of that is and what kind of a force that water will produce at that depth. Okay. All right, so we've got our little guy here, and we've got this rectangle of water. Okay, we want to know what the pressure is going to be on that 1 meter surface here. Okay. We can start by just remembering our definitions, right? The pressure is force divided by area, right? And the force in this case is from the weight of the water. So the force is going to be that gravitational force, which is the mass of the water times that gravitational acceleration. Okay. And for the mass, remember that density is mass divided by volume, and therefore the mass of that water is the density of the water times the volume of the water. I apologize. The pen screen makes these random vertical lines. I hope that's not too distracting. So anyway, so the mass of the water is the density times the volume, okay? And the volume, of course, is the area times the height. Okay, so the volume is the area, which is 1 square meter, times the height, which is 25 meters. So the volume is 25 meters cubed. Okay. All right, so we have determined that the volume of this hypothetical rectangular prism is 25 cubic meters. Okay. And we want to know what the mass is. And remember we said a few minutes ago that the mass is, looks like an arrow, that's a V. My pen screen keeps doing that. The mass is volume times density. Okay? So we know the volume, that's 25 cubic meters, and we should know the density also, right? The density of water, this is a number that you should know, is 1.0, say 1.00 grams per cubic centimeter. Okay. It varies a little bit with temperature, but under most typical conditions, that's a really good number, right? And so we can use that number for the density of water. The only problem with that is if we're going to put that in this equation here, mass is volume times density, our volume is in cubic meters, right? And we've got over, in our density, we've got cubic centimeters. Also, when we do our calculation for forces and pressure, we want to have our mass in kilograms. So we need to take this density here and convert it from grams per cubic centimeter to kilograms per cubic meter. So we're going to have to do two little conversions here. Okay. So let's start with 1 gram per cubic centimeter. Okay. And we want to convert our grams into kilograms. And I hope you all remember that there are 1,000 grams in 1 kilogram. And then to convert from cubic centimeters to cubic meters, we remember that there are 100 centimeters in 1 meter. Oops, I did that upside down. That's a nice mistake, actually. The reason I know it's upside down is because when I go to cancel my units, my centimeters aren't going to cancel because I have both of my centimeters on the bottom. Okay. Let me just scratch through that. I make mistakes like that on purpose a lot, just to make a point. But that was a genuine mistake. Okay. It's still true that there are 100 centimeters in 1 meter, right? But in order to get them to cancel, we need to put the centimeters on the top and the meters on the bottom. Okay? And also, in order to get them to cancel, because this is centimeters cubed, right? That means we have to cube this entire conversion factor. Okay? So that means when we're doing the math here, when we're multiplying this through, instead of multiplying by 100, we have to multiply by 100, and then 100, and then 100. We've got to do that whole conversion factor 3 times. Okay. All right. So if you put this into your calculator, 1 gram times 100 times 100 times 100 for this centimeter to meter conversion here, and then divided by 1,000, what you'll end up with is the density is 1,000 kilograms per meter cubed. Okay. So that's just a unit conversion on the density. To get the mass, mass is the volume times the density, which is 25 cubic meters times 1,000 kilograms per cubic meter, which is 25,000 kilograms. That's a lot of mass. You probably wouldn't have guessed that the mass of the water in this little column right here was quite so high. Okay. All right, so we're almost there. We now know the mass of the water in that column. All we got to do now is calculate the force and then the pressure. So we're really, really close to being done with this one. All right, so we've got the volume and the mass here. Remember that pressure is force divided by area, and the force in this particular case, because it's force due to gravity, is mass times that acceleration. So this is going to be 25,000 kilograms times 9.81 meters per second squared. Which gives us, let's see, 245,250 kilograms meters per second squared. But you remember, I hope, that is that collection of units is newtons. Okay, so the force due to that column of water is 245,250 newtons, and the pressure is 245,250 newtons divided by the area, and the area of this little part right here, because we chose it that way, was 1 square meter, right? So the pressure is 245,250 newtons per square meter, which is 245,250 pascals. Okay. Since our depth, right, that we picked here was given to us in two significant figures, 25 meters, we probably would want to round this to 250,000 Pascal. All right, terrific. It's kind of a long calculation, but that's important. Mostly just from a theoretical standpoint, is understanding how you generate a pressure at the bottom of a fluid from the weight of all of the fluid above you. Okay. All right, so how does that compare to atmospheric pressure, which is the point of this, is what we're trying to get, right? So this guy, this little diver, is standing at the bottom of a lake or something, and there's a whole bunch of water above him, and that water creates a pressure. Okay, we're actually doing something very similar. It doesn't seem like it, but we're actually standing at the bottom of a giant fluid, right? And the fluid that we're standing in is the atmosphere. There are all of these air molecules all around us, and these go up several kilometers, tens of kilometers up into the sky. Right? So there's a ton of air up there, All right, even though we can't see it and we don't really notice it all the time, but all of that air above us creates weight, right? Just like the liquid here creates weight, which generates a pressure at the bottom of that lake. All of the air above us here also has weight, and that creates a pressure that is exerted on us, right? So there's an analogy between this diver at the bottom of the lake and us standing on the surface of the earth. Okay. In fact, somebody, I don't know who it was who said this, but it's kind of a nice quote. We're all standing at the bottom of an ocean of air, and that's really where the air pressure comes from. It's a perfect analogy between what we're doing and what that diver is doing. All right, so since we're using this hydrostatic pressure here as an example to see how, let's see where atmospheric pressure comes from. We want to look at this equation a little bit, and let's develop a little bit of a shortcut that will make this calculation a little bit easier. Okay? We'll start with this definition of pressure. Right? Pressure is just the force divided by the area. Okay? And since the force comes from gravity, right, the force is just the mass times this constant g. Okay? The mass is just the volume times density, right? So we can take volume and density here and substitute it in for the mass, right? But before we do that, substitute here for the volume, right? The volume, just like that prism in the last drawing, the volume is the area times the height, right? So if we take area and height and substitute that in for volume, and then take volume and density and substitute it in for mass, what we end up with is the force. Let's write this over here. Right? The force is the area times the density times the height times g. Okay? And because pressure is force divided by area, the pressure is then going to be the area times the density times the height times g divided by the area. And then these two, the areas just cancel out, right? And so we're left with pressure is the density times the height times acceleration due to gravity. So with all this big mess in here, all those steps we did for that last problem, it all reduces down to this fairly simple equation, and we'll use that to make things a little bit simpler for us. All right, so here's our equation for pressure. There are two different ways that you'll see this. And I think even in this class, I think the Brown and LeMay textbook uses one notation, and the other, the OpenStax, may use a different one. This little symbol here that looks kind of like a cursive P, that's actually the Greek letter rho. And physicists like to use rho for density. So you can see in these two equations here, right? We got D density times hg, or rho hg. Different textbooks write it different ways. They mean the same thing. Okay, so in this equation, D or rho is just the density of the fluid. And here's the important thing. The density of the fluid needs to be in kilograms per meter cubed. Most fluids give their densities listed in grams per cubic centimeter, so you may have to do a conversion factor there. Right. H is the height or distance to the surface of the fluid, and that can be in meters. Okay. And G, of course, is just 9.81 meters per second squared. Okay, so the neat thing about this equation is that it doesn't really matter what the liquid looks like, right? This equation works, and the only thing that's important is the density of the fluid and the height or the distance from the surface. Okay, so this is a neat picture that shows up in physics books. They call it the hydrostatic paradox because it seems really counterintuitive. Okay, and what the hydrostatic paradox says is that you can draw a horizontal line through this at any particular place, and as long as this distance here, this height, and this height, and this height, and this height are the same, then the pressure is the same here, and here, and here, and here. Even though this is a big fat tube, and this one over here is a skinny tube, right? And you can even draw a line down here, right? And even though this one on the far right only has a straight column of water above it, and this one has this little curlicue thing, right? And this one has these two little bulbs. Okay, the hydrostatic paradox tells us, and we're not going to worry about why this works out mathematically. We're just going to use this as a tool. If we draw a horizontal line here, as long as it's a uniform fluid and has a constant density, the pressure is equal everywhere along that horizontal line, and the pressure is given by that equation. All right, so it seems that we could use this equation that we just derived, to calculate the pressure of the atmosphere at the surface. For this little guy, he's standing on the surface of the Earth, and there's all these air molecules around him. We'd like to use this equation to calculate the value of atmospheric pressure. Unfortunately, we can't use this equation directly here, and there are two reasons for that. One is that down near the surface, the air molecules are all very close together, but as you move up higher, they get farther and farther apart, right? So that down near the bottom, the density of the air is very high, but as you move up, the density of the air gradually decreases, right? So this density here is not a constant in the atmosphere. And if it's not a constant, that's going to make it really difficult to use that. Okay. The other problem is H, right? In order to use this equation, we have to measure the distance from this person up to the surface of the fluid. But the atmosphere doesn't really have a surface at the top. It just kind of goes up and keeps getting thinner and thinner until it gradually kind of fades away into nothingness, right? So there really is no H that we can use. Okay? We can still use this equation. It's still going to help us a little bit, but we can't use it to directly measure the pressure of the atmosphere. We need to come up with an indirect way of doing that. All right, so the way we're going to do this is by constructing a barometer. I'm going to show you how to make a barometer. Okay. What you start with is a long tube open at one end, kind of like a test tube, except for this tube needs to be longer. A good length is probably about 1 meter. Okay. And then you fill the tube completely all the way to the top. Fill the whole thing with mercury. And then you get a little dish, and you fill the dish also with mercury. All right. Then to the tube, you take the tube and you put your finger over the top right here so that none of the mercury can spill out. Okay. And then you take the tube, turn it upside down, and put the tube inside the dish of mercury. Right? So you're left with a dish of mercury here, and you've got this tube full of mercury here. Right? And you're still holding your finger over the opening, so you've got this blocked off down at the bottom. So no air can get in there. That's really important. It's essential that no air can get inside there. All right. Now once you've got the end of the mercury-filled tube, once you've got the end of that tube submerged under the mercury, then you remove your finger from the end of the tube and you see what happens. And what happens is when you take your finger off of it to allow mercury to flow through this opening here, some of the mercury flows out of the tube, and so the level in this tube drops a little bit. And this was, people were playing with these in the 1600s, Galileo and a lot of his contemporaries. And what really amazed them, what they were really interested in, was this space at the top. How is there an empty space at the top of that tube if you had your finger over it so no air bubbles could possibly get in there? What's in there? And it turns out that it's not air. Right? What happens is you get this little space at the top, and this space is a vacuum, which means it's an empty space with no air inside it. And the other thing that's interesting is when people did this over and over and over again, the level of mercury always dropped a little bit, but regardless of how much mercury you have in the dish down here, or how tall the glass tube was, the height of the column of mercury remaining in the tube, the height from the surface of the liquid up to here, was always the same. It was always about 76 centimeters. Okay. Or, we'll see this number a lot, 760 millimeters. Okay. That's the height from the surface here to the top of the liquid inside the tube. Okay. All right, now let's take a look at how that tells us about atmospheric. All right, so let's see how we can use this barometer to determine atmospheric pressure. Okay. Remember that there's a column of mercury here, and this column of mercury has a height of 76 centimeters. Okay. Now what we're going to do is we're going to use that idea from the hydrostatic paradox to draw a horizontal line through here. And what we're going to do is we're going to put that horizontal line right at this surface. Since we're touching the mercury here, right, on both sides, we're just in one fluid, right? So we know that the pressure is equal everywhere along that line that we just drew. Okay? So we can break this into two different parts. And let's look over here. There's a pressure over here. I'm going to call this pressure left. And there's also a pressure over here. I'm going to call that pressure right. Okay? And we know that pressure on the left is equal to the pressure on the right. Now the pressure on the left is just the pressure due to the weight of this column of mercury. And remember that there's a vacuum up there. We'll see vacuums like that a lot, and it's important. The vacuum does not exert any pressure. Right? So on the left-hand side, the only pressure that we've got is the pressure due to this column of mercury. Okay? On the right-hand side, the pressure on this surface right here is the pressure due to the weight of the atmosphere pushing down, right? So on the right-hand side, the pressure is atmospheric pressure. Okay? And so what this tells us is the pressure of that mercury column on the left is equal to atmospheric pressure. And even though we can't use our equation, and we have this nice simple equation, pressure is density times height times G. Even though we can't use that to calculate atmospheric pressure by using the density and height of the atmosphere, we can use that to calculate the density in this column of mercury over here on the left. And since the two are equal, that gives us an indirect way of calculating the atmospheric pressure. All right, so what we just decided is that the atmospheric pressure is equal to the pressure of the mercury column over here. That's equal to the atmospheric pressure over here. And while we can't use our handy-dandy equation for calculating atmospheric pressure, we can use that for calculating the pressure of the mercury column. Okay. So the pressure of this mercury column is just going to be the density times the height times G. Okay. And the density of mercury is 13.59 grams per cubic centimeter, which is equal to, I'll let you go back and try that conversion factor that we did before a few pages ago, 13,590 kilograms per cubic meter. Okay. The height is the distance to the top of the fluid, and remember that we said this was 76 centimeters. So this is 76 centimeters, but in order to make our units come out, we want to convert that to meters, which is 0.76 meters. I should point out that on barometers, this height is usually measured in millimeters. So if someone was looking at a barometer and reading it, they probably would say that the height was 760 millimeters. Excuse me. Okay. And G, of course, is still 9.81 meters per second squared. Okay. So that means the pressure 13,590 kilograms per cubic meter times 0.76 meters times 9.81 meters per second squared. Multiply all of that out, and we get 101,300 kilograms meters squared per second, meters per second per square meter. You can play around with the units a little bit to see that that works out, but that gives you 101,300 pascals. Okay, and at sea level, that is approximately atmospheric pressure. There's a slightly, if we had more significant figures in here, we would see that atmospheric pressure at sea level, and I'm putting this here because this is a number that comes up a bit. Atmospheric pressure at sea level is 101,325 pascals. Okay. And this is, I'm putting PATM because that's atmospheric pressure. We did the calculation based on the mercury, but of course atmospheric pressure is the same as that column of mercury. Okay. So this is atmospheric pressure at sea level. All right. We don't usually use big tubs of mercury. We don't usually leave those lying around in the lab. So modern barometers look like this. Most labs will have one. And it's a tall kind of a wooden rack. And it's hard to see exactly what's going on in here. But this is the barometer. It's about 1 meter tall. And right down here in the very middle is a column of mercury. And this part right down here is the reservoir, which has a little pool of mercury in it. Everything is kind of covered up so that it doesn't leak and get out and poison people. But basically it works the same as the barometer that people were looking at back in the 17th century. And if you look up here at the top of the mercury column, you'll see that on the side, over here on the side of this, there's a little scale which reads in millimeters. This is 730 millimeters, 740, 750, 760. And it's hard to see because it's not a very good picture. But this part right here is the top of that mercury column. So on this particular day, it looks like the mercury column was up at about 745, maybe 746 millimeters. That was the pressure in that particular day. Okay. There also are some barometers that look like this, and this is called an aneroid barometer. And instead of having a column of mercury, this has a bunch of springs and a couple of special instruments in it that measure pressure, and then those measurements are converted to this dial out here. Okay. What you'll notice on this aneroid barometer, people like to buy these and put them in their homes because atmospheric pressure actually tells you a lot about the weather. And you can see on this scale, it's got numbers that go around the middle, right, which reads the pressure in inches of mercury or millimeters of mercury. And around the outside, it says stormy, rainy, change, fair, and very dry. And it turns out that when weather fronts come through, the pressure tends to drop. And so when your barometer is showing low pressure, that means that rain and storms are coming through. When the barometer is showing high pressure, that means it's going to be dry and sunny and you're going to have nice weather. And so that's why you'll see on weathercasting, they very often will have weather maps and they'll show the pressure. The numbers here might be a little bit too small to read. In the United States, pressure is usually given in inches of mercury. In Europe and other places, it's often given in millibars. And we're going to look at inches and millibars and all the other kind of units in the next video. But you can see here are the numbers that correspond with the measured pressure at different places, and the H's represent regions of high pressure, and the L's are regions of low pressure, and you can see the low pressure corresponds to this front that's moving through, and that's going to be a place that's got a lot of rain and storms associated with it. All right, so let's take a look at what we discussed in this one. We talked about definition of fluids, right? Both gases and liquids are considered fluids. Anything that flows and doesn't have a constant volume is a fluid. Right? An external pressure exerted on a fluid is distributed equally in all directions. In addition to an external pressure exerted on a fluid, fluids, if they're large enough or if they're dense enough, fluids exert their own pressure as a result of their weight, right? And we saw that with the diver underneath at the bottom of a lake with all the water above them. That water was exerting a pressure because of its weight. And people standing on the surface of the earth are also essentially submersed in a fluid. The fluid is air, and the air also exerts a pressure as a result of its weight. Right? That kind of a pressure is called a hydrostatic pressure. For hydrostatic pressures, we've got this little equation. The pressure is equal to the density times the height, that's the distance to the surface of the fluid, times G. And remember that to use this, the density should be in kilograms per cubic meter. Okay. Since we can't use that equation to measure atmospheric pressure directly, we can measure, I should say to calculate atmospheric pressure directly. We can measure atmospheric pressure using a barometer. And a barometer is a column of mercury in a tube, and there's a balance between the pressure exerted by that mercury column on one side and the pressure of the atmosphere pushing down on the mercury reservoir on the other side. Those two things balance out, and the height of the mercury column gives us the pressure. And at sea level, atmospheric pressure varies a little bit with the weather, but it's approximately 101,325 Pascal at sea level. And that corresponds to a column of mercury with a height of 760 millimeters. All right, good. We're just about through the section on pressure. We've got just a tiny bit more to discuss on pressure, and then we'll start looking at the gas laws.